Before we start the next section, actually it's really nice spring. We have many flowers outside. Actually, in this morning I picked up a magnolia. Okay, magnolia. It's really nice. Okay, it smells very good. Do you have any question before we discuss the relation between the elastic modulus and the shear modulus? So please give me your question in the chatting window. Okay, so now let's talk about the relation between the elastic modulus and the shear modulus using the information that we found from the torsional problem. Okay, as I told you, in the same material point, okay, in the same material point, we can read the stress components differently depending on the observation frame. So if you read the stress condition in the torsional problem, in the reference frame we have so-called pure shear stress condition. But if you read the same stress condition in 45 degrees angle difference, and we have, instead of this shear stress, we have non-zero or normal stress components, but there's no shear stress components here. So if you observe the change in length in this segment, then that should be, if you measure the strain change, the strain change in this direction should be the same strain change in this configuration, because we are talking about the same stress condition. Okay, so I'd like to measure the length change, the strain in this strut. Okay, in this strut. So how do you measure this? So let's say its length is equal to 1. It doesn't matter, you may want to use just the general length L. The length L should be cancelled anyway. Then the initial length, because if you imagine this is square, the initial length should be equal to square root 2. And then this is to calculate the strain, we need to consider the length after deformation, and then the length before deformation. This is the reference length, and then we need to calculate the length length of the after deformation. So let's try to calculate the length after deformation. So initially it was square 1 and 1, and then it is distorted, so it becomes a parallelogram. Okay, so it is distorted. There's no length change, but it is distorted. So for simplicity, I want to fix, I want to rotate the one edge, the bottom edge, to the horizontal direction. Then it becomes like this. Okay, so I want to calculate this length. By the way, when we define engineering shear strain, that was defined as engineering shear strain, isn't it, right? So once we introduce engineering shear strain, this length is equal to what? 1 times the engineering shear strain. So it is equal to gamma. Okay, it is equal to gamma. So then if you look at here, then I have a right triangle here. Then let's use Pythagorean theorem. Then the length here in the bottom is equal to 1 plus gamma. Okay, this is the bottom length. The height is equal to 1. Then how do you calculate its length? So using Pythagorean theorem, its calculation becomes very simple. Square root of this quantity, isn't it, right? So this is a definition of strain. Okay, now let's approximate this quantity by using the concept that engineering shear strain is very small. Let's use Taylor expansion up to the first term. Taylor expansion, Taylor 급수, probably, yeah. Then if you do that, we can approximate to this equation. Here 1 is cancelled. Then finally the maximum maximum strain in this direction is given by 1/2 engineering shear strain. This is a relation between the maximum strain in the diagonal direction and then engineering shear strain here. So now let's try to use the Hooke's law. So if you use Hooke's law, then the strain is what? The strain caused by this tensile normal stress is because its magnitude is given by tau divided by elastic modulus. And then we need to calculate, we need to consider another strain change in this direction by the transverse loading. The transverse loading is here minus tau. So minus tau, okay, the minus tau divided by elastic modulus, and then we need to multiply the Poisson's ratio because that is the definition of Poisson's ratio, isn't it? And then we need to subtract. So here, then we can, we already calculate the maximum normal strain is equal to a half of engineering shear strain. Let's make them equal to each other. Then what happened? So, according to the Hooke's law, in the shear strain and shear stress, this is given by tau is equal to shear modulus times the engineering shear strain. Then, this is equal to what? Maximum strain in the diagonal direction is equal to the half of engineering strain, and then the shear stress is replaced by this constitutive relation. Okay, then let's rearrange this equation. Here make sure that here the engineering strain can be cancelled. That's why we can conclude that shear modulus can be given in terms of elastic modulus and then Poisson's ratio, which means the elastic modulus is not independent of the shear modulus. Okay, so once we have elastic modulus and Poisson's ratio, then we can calculate the shear modulus, the vice versa. So if you have shear modulus and Poisson's ratio, then we can calculate the elastic modulus. So which means in the linear elasticity, there are only two material parameters. Okay, elastic modulus and Poisson's ratio. Okay, this is the conclusion in this section. Do you have any questions? Oh, Yujuni, sorry, I missed your chatting. He said, yeah, I forgot the sign convention of shear stress component. The sign convention of shear stress component is what? Say if you have a reference material point, and then it is always important to introduce a coordinate system. So if we have shear stress component in the positive direction on positive side, okay, on positive side, then this is the normal. Sorry. Okay. First we need to identify normals. Sorry. First we have to introduce normal. This is a normal indicating the direction of this plane, and this is a normal. This is normal, and this is normal. If my traction is on the positive plane in positive direction, okay, then we want to say that this is positive component of shear stress component. And also here, so on the positive side, okay, positive plane, and then to be positive should be in the positive direction here. And then in negative side, so negative plane, the shear stress component should be in the negative direction, okay, then it's overall positive. So summarizing, the positive shear stress component look like this. This is positive, the positive, negative, 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 negative. Then it's positive. Then this is negative. Okay? The sign convention of shear stress components is given in my lecture note. So we already discussed a long time ago, actually. This is the sign convention for the shear stress component. Shear stress acts on the positive face in the positive direction of a coordinate axis. Then we'd like to say this is positive. And also the combination of negative and negative. That is also positive shear stress component. But if sign is opposite, like the shear stress acting on positive face, but is in the negative direction of the coordinate, then it is negative. Eugenie, is it okay for you? Any other questions? Good. Okay, so next time we will talk about the energy in torsion. Okay, energy in torsion. So let me stop my lecture here.